The practice review for test number 2 is already posted, and it's going to cover potential, so the unit about potential, and then the unit about capacitor, it's a very short one, and circuit. So 3 units. It's like 2 units because capacitor is part of circuit. Okay, I have already posted the assignment, so please save your memory, your USB, physics USB over spring break. Don't forget everything. Okay, so last time I went a little bit fast over capacitor, so I just want to review. Okay, and it's good to review. At least using your textbook. So I've said 2 things I want to review to make sure that it's clear. So first thing, and it's a review also, right? Remember the electric field derived from a potential. So if it's in 1D, okay, it's just you have to take the derivative, which means the slope. If it's in 3D or 3D or 2D, that means that the electric field will be the steepest slope of the voltage, right? The equipotential. So if you reverse, that means that if you have the electric field, then the voltage, and that will be a property of 2 points. Okay, so it's potential difference. You have to integrate. So if it's 1D, it's easy. And that comes from because voltage is energy per coulomb. So that will be the work that you have to do against the electric field to increase the potential energy. So it's a work, right? It's a definition of work. If you are in 2D, for example, then you just have to use the dot product. Okay, so if you have, this is a voltage, so if you have the electric field, all you have to do is to find the integral to find the voltage difference. Okay, so I went a little bit fast over that. And then about dielectrics. Okay, we were talking about dielectrics. So let's say you charge. Okay, so you charge your capacitor. You can put everything here. You can show the electric field. So if it's connected, and then it's going to be in the pop quiz. If it's connected and you shove inside the dielectric, the electric field is not going to change because you are able to bring more charges, right? You're going to get more charges if you shove the dielectrics here. The capacitance is increasing. So you are increasing the capacitance, you are increasing the charge, and you are increasing the store energy. Okay. However, that's on the pop quiz, in the pop quiz, and it connected to the story with the fish, electrolocation, something like this. So if it's not connected, if you have an electric field, so for example, in the case of the fish, here there is, I don't know where the fish went. Where is the fish? Always lose it. Fish. One fish, but it's not the right one. This one. Okay. So if you already have an electric field, which is produced because of distribution of charges, ions, electrolytes. So there is an electric field here. So if you have an electric field, and then you shove between the plus and the minus, so you shove inside the electric field an insulator. Now, what you can see is that it will weaken the electric field. Okay, so an insulator inside an electric field will make the electric field weaker. You see the lines are more spaced out. Even though the capacitance is increasing, nevertheless, the charge cannot change because it cannot go anywhere. Store energy goes down because the electric field decreases. Okay, and the energy is proportional to E squared. Okay, so if you already have an electric field, you have an insulator inside the electric field, now the net electric field will be weaker. Okay, that's in the pop quiz, but it connects connect to electrolocation, right? So if you have already an electric field and you show here an insulator, which is like a dielectric, inside here, you're going to have some polarization happening. So we already discussed what is going on here, but you see that the electric field get weaker, and that's how the sensor in the brain of that fish will know that's not good to eat. If you have a conductor, because electrons are free to flow, it will make the electric field stronger. Okay, so I wanted to make sure you get that right for the pop quiz. Okay, so that's the story of the fish. And then here, so let's review capacitors just to make sure you know how to do the homework. Let's go back to your book. It's a great book. Okay, so here that will be chapter 24. So it has here the definition of capacitance. So the unit is in farad. So it's named after Faraday. That will be the amount of charge that you can store for per unit volt. Okay, so per 1 volt. That capacitance here only depends on the geometry of your capacitor. It only depends on the geometry because capacity means volume. So if you want, you can, here, you see, you can think of beakers here. You have different capacity. So here, of course, you're going to store more liquid, and the same thing with capacitors. A capacitor with a larger capacitance, like this one here, will be able to store more charge for the same voltage applied. Okay? So a tiny one, it's not going to store as much charge than the big one. So capacitance, think of capacity. Okay, and if you take your book here, you have it's explained. Capacitance is a measure of the ability of a capacitor to store energy or to store charge. Okay? And remember that you need to know how to use this equation sheet. You see that the energy store will depend on the charge here. Okay, it will be actually proportional to the charge square. So you double the charge, energy store will be multiplied by 4. Okay, so it's a review from last time because I took the bullet train. I went very fast. So I'm just reviewing. Okay, what else? Okay. So then we talked about the parallel plate capacitor. So that's what you have to deal with when you are doing circuit and electronics. And you see, how do we find the capacitance for a given geometry? So first you write the equation. Okay, so the definition, capacitance is going to be the charge over the voltage. So the voltage will be between one plate and the other plate, right? It's a property of 2 points. So then the charge you already know. So you need to find the voltage. How do we find the voltage? Okay, so it will be between the two conductors or the two electrodes. How do we find the voltage? You use the definition here. Remember, you go back to here, you see the voltage is the integral of the electric field. So if you have the electric field, which you have using Gauss law, okay, and the geometry is always very simple, it's using symmetry. If you have the electric field, then you can find the voltage. Okay, so in that case, remember the electric field between parallel plates capacitor is uniform. It only depends on the density of charge, right? That will be the definition. So it's a constant. So if you take the integral, you just multiply by x. Okay, so that will be the distance between them. Okay, you integrate between here and there, so you multiply by x. So that will be the voltage between the plates. You already know that, right? The voltage is the electric field times the distance between the plates. That will be in your equation sheet, or you take the integral. So once you have the voltage, then you use this equation. Capacitance is Q, so the charge that is stored over the voltage. Okay, so you divide by Q, and that's what you get. So for a parallel plate capacitor, the capacitance is proportional to the area, inversely proportional to the distance. So again, the capacitance only depends on the geometry, anything else. Because capacity is like the shape of your reservoir. So parallel plate capacitor is the best to store a lot of charges. Right? And I'm lost. But it's okay because I have my notes. Okay. Okay. So a lot of applications, for example, you have this beautiful woman who is singing, whatever she's singing, but it's a microphone. And inside here you have a capacitor, and the same voltage is applied to the capacitor. However, when she's singing, you're going to have a sound wave. The sound wave will push on the plates of the capacitor, so the distance will change, the capacitance will change. So if you increase the capacitance, that means you can fill it more with charges. So more charge will flow, you have an electric current, and then you have a signal. So it works like the keys of your keyboard. Okay, so that's a nice application. Okay, epsilon zero. So again, farad is the unit for capacitance. That will be what it means. Epsilon zero is a constant. Okay, we done that, did that. So for example, here you can so when you are working to study for physics, and especially if you're an engineer, you have to hide the solution. You can not look at the solution. You have to hide it. You have to work on it, and at the very end, you can look at the solution. Okay, so here you have more practice, which is nice. Okay, blah, blah, blah. Okay, so here they show you how to find the capacitance of a spherical capacitor. Example, a Van Graaff generator. So Van Graaff generator will be that sphere here, the inner sphere, which is charged positively, let's say. And the outer sphere will be far away, will be the wall, the ceiling, the ground, and that will be all connected to the ground. So that will be your minus. Okay, and you have the electric field. So how do we find the voltage? We need to find the voltage to be able to find the capacitance. And you do that because you know the electric field. And how do we know the electric field? We know it because of Gauss' law. Okay, so remember when you have two spheres here, so you're gonna have the electric field going this way, that way. You cannot have electric field inside. Remember Van Graaff generator, inside here the electric field equals 0, but the electric field is uniform in magnitude. Here it goes radial, it goes from plus to minus, and that will be very far away. For example, that will be the ground. How do we find the electric field? You already know that, so it's a review. You take a imaginary bag, a spherical bag, okay? And you're gonna say E times the area, it's gonna be Q in over epsilon 0. And if you do that, you find that the electric field will be K, Q of this Q here. So here you have minus Q, and here you have plus Q, it's a capacitor, over the distance here, that over that where you are here, that distance here, r square, from the center. So it means that the electric field does not care about this sphere. The electric field only cares about the source here. That's a consequence of Gauss' law, which is a consequence of Coulomb's law. So how do we find, so you have here, this is A and this is B. So that will be voltage A and that will be voltage B. Okay, so they have a different voltage, the inner sphere and the outer sphere. How can you find the voltage? So then you integrate, okay, from A to B. So again, how do we find the electric field? The voltage. How do we find the voltage? You integrate. And I don't worry about the sign. It should be a negative sign, but it's a headache. You know that voltage will be larger than that voltage. Okay, so then you have, when you integrate, you're gonna find 1 over R, and you already know that, right? The voltage of a point charge is gonna be 1 over R. Okay, and that's gonna be KQRB minus KQRA, and you have to be careful at the end that this voltage is higher than that voltage. But that's how it's done. Okay? So I'm putting more details on what we did last time. Last time I just gave you the equation. Now I'm showing you how to do it and how to use calculus. So you see, that's what they did. Okay, so they find the voltage here between this sphere and that sphere. Again, a voltage is a property of 2 points. And on the conductor, the voltage will be the same all around. So you find the difference in potential, so the voltage here, and then you use a definition for capacitance, so Q over the voltage, and that's what you're going to get. And you see, it depends only on the geometry. Okay, only on the geometry. So I wanted to show you the calculus now, because otherwise you will have been too overwhelming last time. So you have two conductor RA, and that experiment was done by Faraday, right? RB. Now, if you put RB like very, very, very far away, so that will be the ground. So now you have just either you have the Earth, okay, so the Earth, or you can have a Van Graaff generator. So in that case, RB is very large over RA. So you're going to have 4 pi epsilon 0 RA RB, and then RB is very big. Boom, boom. It's going to be 4 pi epsilon 0 RA. So you have one equation like this on the pop quiz. So that will be the capacitance of an isolated sphere, such as the Earth, a balloon, if it's uniformly charged, or a Van Graaff generator. Okay? Are we good? Example here. They give you and this is picofarad. Okay. It's a very nice book. And then you can do the same thing for a cylindrical capacitor. So first you find the electric field like we did for the last unit. Okay. Remember the last unit we used Gauss law. So you find the electric field and then you take the integral to find the voltage. And then you use the definition for capacitance. Okay, so it's the same thing as before. So if it's two conductors, it doesn't matter if it's a cylinder or just a wire. It could be a corona wire. You know, you have that in a Xerox machine, copy machine. You have a wire here, charge, and then it can be discharged on the drum or whatever, how it works. But it's the same equation. You have the electric field will be lambda, which is the line, the linear density over 2 pi epsilon 0 r. Okay, r will be the distance, so that will be the electric field here. R will be here. Okay, from your equation sheet. Okay, that was last unit. And if you take the integral between a and b, okay, 2 pi epsilon 0 r. And what's the integral of 1 over r? ln. Yeah, it's ln, right? So it's going to be A to B ln between A and B. And you don't have to worry about the sign because at the end, you know that the positive will be at a higher voltage. So you can adjust at the end. So when you do that, that's what you're going to get. ln, because ln, you know, of this, when you subtract log, it's going to be the log of the, okay, from math. Are we going? Okay, it's nice application. Okay, so you have your voltage. Okay, the voltage property of 2 points, and and then you can find the capacitance. Okay, you do this, and at the end, it depends only on the geometry of your of your cable. It's a cable. It's a coaxial cable. So a lot of applications in engineering because all those charges that build up on your cable will slow down the signal, especially if it's a high frequency signal. So for a cable, we can find the capacitance per unit length, and that's what you're going to get. Okay? So it's a very nice book, blah, blah, blah. Okay, you have capacitors here. So you can have capacitors in parallel. So in that case, you are boosting the charge. Okay, the charge will add up. It's the opposite that for the resistance. So we can find the equivalent capacitance. When they are in parallel, you weaken. You're going to make the charge. No, what did I say? It's the opposite, right? I'm rewinding. Rewinding. In series, you weaker. It will make the capacitance weaker. In parallel, it will make it stronger. So in parallel, the charges will add up. Series. And the equation is that you add the capacitance. So everything happens like you have one single capacitor here, and you add the charges. Okay? I want a little bit fast. Okay, it's fine. Okay, what else? Blah, blah, blah. Blah, blah, blah. Okay, in series, in parallel. Okay, have fun. It's interesting. Okay, and then you can store energy in a capacitor. Okay, and you see that the energy store is proportional to the charge square. So you double the charge, the energy will be multiplied by 4. Okay, and you have those equations here. The energy store inside the parallel plate capacitor will be, you can play with the equations, but these are the equations here, and you see it's proportional to the charge square. Okay, blah, blah, blah. A lot of applications. So here there is a interesting application. There is something called the Z machine. And it's so now nuclear fusion is very hot. It's very, very hot topic. Everyone is working maybe secretly, like a lot of things is classified on nuclear fusion. And so here in New Mexico, they have what is called a Z machine. And they use capacitor to store a huge amount of charge. And a capacitor, one of the things is that they can burp out that energy in a very, very small amount of time. So it can burp out a very large spike in current. That's why it can kill. Now, a coil inductor can store energy in the magnetic field, but that energy can be burped into a very high voltage. So it can provide sparks. So you have similarities. So anyway, this is called a Z machine, and they store energy into capacitors. And then you can do the computation here. We have what is called the energy density. Okay, so that will be the energy stored in an electric field per volume. So the energy per volume. And it's stored inside an electric field, and it's E square. Okay, so it's proportional to the electric field square. Okay, some people went on spring break earlier. I will help you for the pop quiz. Okay, that's. If you need help for the pop quiz, let me know. I will give you the answer. But don't share, okay? You don't share and you don't care because it's not kindergarten. Just for yourself. And then here you have nice problems. It's a very nice book. And then you have about dielectrics. So you see what you can imagine a parallel plate capacitor looks like. So you need to have two conductors, and then in between you have a dielectric, so insulator. And then what you do, you hold that up, so you're going to increase the area, so you increase the capacitance. Yeah, so that's the old one. So the new one, they use juicy stuff, so I don't know the technology, but for the PCB, they make it they can make it as on the waffle, silicon waffle, and they print them out. So it's another technology, but it's the idea. Okay, so so the capacitance will be boosted with a dielectric, and that's what I told you. The electric field get weaker because of the polarization, but we already talked about that. But at the end, the capacitance will be boosted by a factor K. Okay, so instead of having just epsilon 0 times the area over the distance between the plates, it's going to be boosted by a constant K, the dielectric constant. And you have some values there. Okay, so Teflon is 2.1, vacuum is just 1, mica is good. So you have different values here. And so sometimes just a notation, instead of writing K epsilon 0, it's going to become an epsilon. So epsilon is just K times epsilon 0. So it's going to boost the energy as well. So the energy will be multiplied by factor K. Okay? I think it's good. Just introduce the concept and then you dig more into details. And then it becomes more complicated. Here you have a nice application for the cell membrane. So everything in the body is about charge distribution. It's electrical, even though they don't want you to know that if you're in biology, but everything is physics in there at a small scale. And then it becomes more complicated. If you like calculus, you can do that. And then here you have a nice summary. Okay, done. Any question? So for capacitor will be very simple for the test, right? So we were talking about DC circuit, just the fundamentals, and I think it's an easy unit. So basic circuit, you're gonna have a power supply. Power supply will give you the voltage. The voltage will be energy per coulomb. So if you have a 9-volt battery, each coulomb of charge leaving the plus here will have an energy of 9 joule. Imagine it's positive coulomb. So 1 coulomb of charge, each coulomb 9 joule will deliver the energy to the load, and then it comes back here, no more energy, and then it gets a boost again. Okay, now you can have more than 1 coulomb per unit second. The amount of coulombs per second, that will be the current. So I will show you that for a simulation. Once you understand the concept, everything else is just math. So here you have a hydraulic system, you have the pump. So the pump is like the power supply. It's going to increase each gallon of water to a higher potential energy. So potential energy, gravitational potential energy, that will be electrical potential energy. Okay? And that energy can turn into kinetic energy. That energy can turn into light, into sound, into motion, and then it comes back and get a boost again. So voltage, you can think of that as altitude, right? Now you can control the amount of water flowing with a valve. Okay? So it means that if you have more water flowing, you're gonna have more energy delivered during the same time. So here for a circuit, we're going to talk about the number of coulombs per unit second delivered by the power supply. So that will be the current. You can control that amount of current with what we call a resistor. So a resistor is like a valve. Okay, you can increase the coulombs or decrease the coulombs. So here you have a very simple circuit here. See, you have the power supply. So in reality, the charge carrier are electrons. But we're gonna pretend we don't know that because we love Franklin Roosevelt, right? And we're gonna say it's coulombs. It's easier to understand this way. So we're gonna pretend that the power supply is delivering coulombs. So each little thing that you see here is 1 coulomb. Every coulomb has a potential energy of 30 joules. Okay, the voltage is a property of 2 points. So you have chemical potential energy turning into electrical potential energy, so 30 joules per coulomb. So if you are measuring the current, and in real life, it's not that way, it's just to understand. But you see, I can measure the current here. So it's like you have a little thing inside, l'impression, something like this. So every second, it's counting how many coulombs passing by. 1, 2, 1, 2, 1, 2. So 2 coulombs per second. That will be the definition of the ampere. Ampere was French. Ampere. So I know I say it right. Amps. If you want to look cool, you say amps. 2 amps. Okay, so that will be 2 amps. So 2 coulombs per second, and it will be the same even inside here. There is no leakage, right? It will be 2 amps everywhere. Agree? I can use this as a way to control the amount of coulombs per second. Or we can think of that as a speed. Okay? If I decrease the resistance, so decreasing the resistance here is like you're decreasing the size of the pipe everywhere. So you make it harder for the current to get through. So if I increase the resistance, okay, you decrease the size of the pipe, and now you see it's going to flow slower. The amount of coulombs crossing this intersection is going to decrease. So it's like a valve, but it's going to decrease everywhere. And if I decrease the resistance, then it's going to flow faster. Now I have 3 amps. So 3 coulomb per second, that will be the current. So it means it's going to be brighter. Why is it brighter? Because I have more energy delivered per second. So let me ask you something. You have 30 joule for 1 coulomb. But you have 3 coulomb per second. So how many joules per second? So 30 joule per coulomb, and you have 3 coulombs per second, 90. Okay, so you have 90 joules per second delivered to the load. And what is joules per second? Watt, right? Wattage, yes. Okay, so that will be the energy consumed per second. So in that case, you have only one load, so that will be the energy delivered per second. So power is voltage. So the power delivered by the power supply will be the voltage times the current delivered. Does it make sense? You see, if I make it if I decrease the resistance here, it's gonna go even faster. So energy is being delivered faster, higher metabolism. It works like us, right? When you are young, you are not insulin resistant, you have a very high metabolism, so you burn the fuel very quickly. If we get older, it looks like this. Right? And if you are very, very young and restless, that's what's going to happen to you, right? So there is no more resistance. You are not controlling the current anymore, and you start a fire. Now the fire. Dun, dun, dun. Okay, so you get the idea. Are you with me? Okay. Okay, so changing the band in the real life, you have yes, exactly. So it used to be that students had to learn by heart the code. There is like one is the 100, the 10, the 1, and then the percentage error. So if you are in electronics, maybe you know the coding code. So how, they have you find the resistance? Oh, okay. Oh, the percentage. Oh, I see, I see. So it's interesting because the 5% are more expensive than the 10%. Right. So that is called a resistance. But that's good you did the lab. So it's a resistor, it's a component, it's a load because it means it's going to consume the energy and turn that into heat. And my experiment is that if you have a resistance which is too low and then you touch it, you burn. You burn your fingers. You have to be careful with those. But any load that you have has inside like a small, it's like you have a small sneaky resistor inside. So some of the energy, like energy will also turn into heat. So any load that you put, you see I can have here. So if I decrease the watts of the light bulb, you see that's what it does. So if you have a 100-watt light bulb, that means the resistance will be smaller. If you have a 40-watt light bulb, the resistance will be larger. Does it make sense? So it's everything in a nutshell. Because once you understand the idea, then it's not going to be hard. I wanted to have a nice number here. I'm going to decrease this one. Ah, 2. Don't move. Okay, perfect. And then measuring voltage is like you are measuring height. So it's going to be between 2 points. And we're going to talk about voltage drop because I will show you a way how to solve the circuit. But you have to think of voltage as a altitude, a voltage drop between 2 points. Don't forget, it's always between 2 points. So if I measure the voltage, of course, if I measure the voltage across the power supply, of course, you're going to find 30, right? It makes sense. if I measure the voltage across that load here, okay, so I'm measuring the drop. So you start by 30 and now it's going to drop. What's the voltage? 6. What is 3 times 2? 6. So this is called Ohm's law. So the voltage drop across a load, it's going to be equals to the resistance here of the load times the current going through it. Ohm's law is not a nature's law. It's not like F equals ma, because it works only for some loads. So if you have semiconductor, for example, LED, it does not work. It works only for ohmic components. So it's like more a trial and error, like it works, but it's not F equals ma. It's not for everything. Yeah.
You said it only works for what?
For ohmic, like component, it's called ohmic components. So it means loads that you can replace by a resistor. Okay, it doesn't work like if you have a LED. This is a LED, it doesn't work. Or if you have an op amp, anything semiconductor, things like this, doesn't work. Or a transistor, it doesn't work. I forgot how to make a transistor symbol, but it doesn't work because it's semiconductor. Okay, so listen, you have 30. Start with altitude of 30. You drop by 6. How much is left? Huh? 24? Let's see. 24. Okay. Now, it's not because this one comes first that it's going to take everything. It's not a first come, first serve. Doesn't work that way. It depends on the resistance. So this is called a circuit in series. And with a circuit in series, the one with the larger resistance will take all the voltage. It's going to steal everything. So this one is taking everything, so more energy, because it has a larger resistance. So that's why in a house or in a room, you never use a circuit in series. You never do that because the one with the more resistance will take all the voltage, and then nothing is left for this one. Okay? Agree? And then you have 24 plus 6 equals 30, which is called Kirchhoff law for voltage. Okay, so this is circuit in a nutshell. So the trick is, because some people, if you are in electrical engineering, you have to take a class called circuit or something like this. But here is the trick. So the book will say, okay, you have a 30 volt here, and then you have a load here, 3 ohms, and then you have another ohm here, 12 ohms, and here, and you put your voltmeter, blah, blah, and you have a 6 volt, and here you have 20 volt. Instead of doing that, and it's going to be useful for more complex circuit, what you do, you start with your power supply, which is 30 volt, and you think of it as an altitude. So it's called a schematic. That's what they do in engineering. So 30 volt, it's high up, high hill. And then you go first load here, that's going to be 3 ohm. You go take a walk, boom, 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 nothing happened. Up, 3 ohm. So you have your 3 ohm. Boom, 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 nothing happened. And then up, you have a 12 ohm. And then boom, 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 you go back to base. And I'm going to call the base the ground. So that's going to be the ground. Okay. Now it's easy to see that it's like water flowing. See? Water wants to flow this way. And the water here is 2 amps. And then you're going to have a voltage drop. So from 30, boom, 6 volt. And then boom, 24 volt. And if you do that, it's called a schematic. And if you're doing electronics, that's how it works. Okay, that I call that the base or the ground. And then the power supply boost it up again. Okay, so that way, if you have a circuit in parallel, you can do the same thing, and it's going to be much easier to solve. You can so have something like this, and you go back to base, but you have a voltage drop, and you have a voltage drop. And then you have something flowing here, and you have something flowing here, and you have something flowing there. And imagine these are pipes uphill, and then you go back to here to base. So if you do that, it's going to be so much easier to solve the circuit. Okay? So it took a little bit of time, but then it will be easier. Okay, so this is a load, power supply. Okay, got it. The source for energy in a power supply is called the EMF. Okay, so if you have a car battery, you have a voltmeter, you're going to read 12 volt. But as the battery gets older, you still have the same EMF 12 volt, but if you put a load, you're going to see the battery is going to steal. It's going to take away some voltage. So instead of having 12 volt, when you have a load, you're going to have 12. Instead of having 10, you're going to have 10. But anyway, we're going to see that. So it's called the EMF. So sources of EMF, you have batteries, power supply, solar cell, fuel cell, and lemon. If you want to do a lemon for extra credit battery. So this is the idea. Each coulomb of charge, okay, the battery. So if you want to create a voltage, you have to do work against an electric field. So here the battery itself is doing work through chemical reaction against the electric field. So the coulomb of charge is raised to a higher potential energy, so 1.5 joule, for example, per coulomb, and that energy is delivered to the load, and you can change how many coulombs is produced per second. Okay, so we're going to pretend we have coulombs flowing. So each little sphere is 1 coulomb. That's we're going to pretend. That will be the definition of current. So the current will be how many coulombs crossing through this imaginary surface per second. So it's a rate. So you can imagine this is a speed, how fast it's flowing, right? The unit is amps. So then you have direct current from the plus to the minus, and you have alternating current, AC. That's what you have from the outlet. So from the outlet, the electricity, the current is going back and forth, back and forth, back and forth, 60 times per second. So 60 hertz. In Europe, it's going to be 50 hertz, but we cannot do anything like everyone else. It has to be 60 here, and Europe it has to be 50, and South America mostly 50 as well. We are special. Okay, so charge carrier. Responding to an electric field, because inside the circuit you have an electric field that will move the electrons. So in a circuit, it's connecting wires, you're going to have electrons flowing, but it doesn't have to be electrons. Inside the body, for example, you're going to have electrolytes, plasma, it's going to be ions, electrons, semiconductor, you have holes of electrons, and then it becomes more complicated here. Okay, so conventional current will be positive coulombs. So each one is a coulomb, and it will go with the electric field. So each time a charge is moving, it's because you have an electric field. In reality, it's really electrons moving against the electric field. But this is conventional, and it's easier to explain. Okay, some typical current. See, current kills. It's not so much the voltage, it's the current. Okay. Okay, so the equation that we're going to use, time will be in seconds. So if you see minutes, you have to convert to seconds. Energy will be in joule. Charge will be in coulombs. Current will be the amount of coulombs per second, so Q over T. Voltage is a property of 2 points, so it's a drop. Voltage is a drop. Voltage is a drop. Think of it as a drop. It's going to be joule per coulomb. Power is the energy consumed by a load produced by a power supply. It's energy per second, and the unit is the watt. So watt? It's a watt. Joules per second. Okay? And then we're going to have resistance R, and the unit is ohms, right? And the symbol here is omega. And you have this equation. So power is voltage times current. We did that previously, blah, 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 blah. And this is Ohm's law. The voltage drop across a load is the resistance times the current. Okay, electric circuits, you see you have capacitors here, and you have resistors here, and you have an inductor there. Okay, so how do we measure current if you don't blow a fuse? It has to be part of a circuit. Okay, so when I do that, it's just to explain that does not exist. You don't have such thing. This is just for the sake of explaining. You need to open the circuit, and the ammeter or the multimeter to measure the current has to be part of a circuit. And it's 2 amps. It has to be part of it. So inside here, they hire a graduate student paid minimum wage, and it's all it does is counting 1, 2 per second, 1, 2 per second, 1, 2 per second. But you don't want that device to disturb the circuit, right? So that device to measure the current needs to have a very, very, very small resistance. Otherwise, it's going to disturb the rate here. So ammeter or multimeter in the current setting has no resistance, which could be very tricky because some students, because they don't listen, that's a student thing, right? They don't listen that much. What they will do, I've seen that so many times, they will put multimeter to measure current as a short. And that will be very bad because you are making a short. So the current wants to take the path of least resistance because it's lazy. If you say go this way and this way has to push and go that way, but this way is going to be much easier, it's going to go, most of the current will go through here, right? And you see this is not even working anymore. That's called a short. And if you do that, you blow a fuse. And then someone has to take a screwdriver and change the fuse, which is very annoying. So this is called a short. Okay, so that will be for an ammeter. Now a voltage is measured by a voltmeter. So in that case, you are measuring the drop. It's like a measuring tape. So when you are measuring voltage, you take your voltmeter and you go across. Okay, you go across. Now, a voltage, you don't want to make a short. So a voltmeter will have a very, very large resistance. It will be the opposite. A voltmeter will have a large resistance, so nothing can be deflected. Some will, because you need to do the measurement, but otherwise you have to use another technique to measure the voltage. But very, very large resistance, right? So if I open the circuit here and I place that in series, is there anything flowing now? No, because this one has such a large resistance that no current can flow. So if there is no current through that resistance, there is no voltage drop. There is no voltage drop here because it's R times I. So so this is like a dead connecting wire, and this is a dead connecting wire. So you are just measuring the voltage across the battery. So if there is no current through a load, there is no voltage drop. See if I measure the voltage drop now across here. Okay, nada, nothing. Okay, nothing. Okay, and now I ruin my thing. Okay, let's do some. So can help each other. Let's do this one. Using the definition. So look at your equation sheet from the previous slide if you need. So that will be a voltage drop. So the definition for current is how much charge is flowing per second. Right, so it's going to be so it will be the time times 0.17 times 10 to negative 3. Do you get that? Which is 612 millicoulomb. And then how much energy? So you can do it different way, right? You can say, okay, the voltage is the energy per coulomb. You can do it this way. By definition, the voltage is the energy. Voltage is potential energy per coulomb, for 1 coulomb.
Uh, 1.8 resistors acting within
Yeah. Okay, did you all get that?
Yes.
That will be delivered, total. Now, another way to do that, you can say power. You can say that energy is the power times the time. Okay? Or power is energy over the time. And the power is the voltage times the current. So instead, you can use that equation here. Okay, power is voltage across times current through times the time during which the current was flowing. And you will get the same thing. So you can do it 3 times 0.7 times 10 to negative 3 times 3600, and you get the same thing. Okay, so you can do it a different way. Okay, it's gonna be easier because you already did the lab. I think the lab are very good. Okay, so then we have what is called the electric resistance. So you can imagine that if the resistance is going to increase, it means it's like a pipe, right, through which the coulombs are going. You can make it tighter or wider. If it's wider, you're going to have more current flowing. You can think of that this way as well. So you take 1 coulomb of charge, you are doing work against the electric field, and then it goes downhill, but you can increase the spikes here. Okay, so you increase the resistance. The unit is in ohms. Okay, so this is very, very true across biology or thermodynamics. So you have voltage equals current times the resistance. So this is a drop. So it means that, example here, thermodynamics, you have hot and cold. So the heat is energy in transfer. It goes from hot to cold. The amount of heat that will flow depends on the difference in temperature, delta T. So if it's very cold inside because you blast the AC, and outside is the opposite, very, very hot, you're going to have more heat loss, right? It's going to cost more money because heat will flow more from inside to outside. You're taking heat away. So the amount of heat that will flow is proportional to the difference in temperature, but it also depends on the material in between. So if it's an insulator or not an insulator. So you have an input and then you have output. Input will be the difference in temperature. Output will be the heat, and it depends on the material between them. Likewise, water flowing down there, it depends, of course, on the height. Okay, more height, more pressure, more water will flow, but it depends on, the valve, if you have a valve or not, right? So same thing here. You always have the stimulus and then you have the output. So here, a voltage is like pressure, okay? The motivation, the stimulus. So more voltage, more current will flow, but it depends on the resistance here. So the current that flows through a load depends on the voltage drop, it's like the pressure, the motivation, but it's also depending on the resistance, so inversely proportional to the resistance. So a student of mine, that was last semester, she made the connection with, because she's taking the MCAT, and she made the connection with the human body. I don't know which field is that, cardiology, whatever. But you see, you have the same kind of relationship. So you have the amount of water, but not blood. It's the blood per minute. And they call that cardiac output. So blood per minute depends on the blood pressure, which is like a pressure, right? So it depends on that. But it's also inversely proportional to the resistance to blood flow. So if how tight those what is called arteries are, right? The pipe system. So it's exactly the same equation. Isn't that interesting? And that's how she remember. She remember because she was applying Ohms. So V equals RI, and here you have exactly the same thing. The amount of blood depends on the pressure, but it also depends on how tight those arteries are. It's the same idea. Okay, so Ohm's law. Okay, so the voltage drop across a load equals to its resistance times the current flowing through. And again, Ohm's law is it just applies to some loads, not all all the loads. So it's a linear relationship between the current and the potential. So you increase the potential difference across the load, you're going to increase the current. It's a linear relationship. Okay. Now, if you have a semiconductor, it's a whole different story. You cannot apply Ohm's law. So if you have a diode, no current will flow until you hit a threshold. So for a blue LED, for example, it's going to be about 2 volts, and all of a sudden, boom, you have an exponential growth here. It's not under control anymore. So that's why you always want to protect a diode with a resistor, because otherwise it's not under control, it's out of control. So when you are working in electronics, you have to use I don't know for how it's called. You have to use the paper that goes with it and describe how the current will respond to the voltage, right? Okay, so lots of application in human body. Very nice application is around the neurons, okay, that makes our nervous system from the brain to whatever it goes, to the muscles, for example. And they talk to each other through synapses, but around those neurons here, you have a layer, and that layer is called myelin. And myelin is a resistance. It has a very high resistance. Why is that? Because the signal is electric. It's an electric signal going through the nervous system. It's polarization, depolarization, so it's a wave of voltage. Okay, and you don't want that signal to leak out. So you need a very, very good layer of myelin to prevent the signal to leak out. So it has a very large resistance. That's going to be a resistance, right? So it works the same way when you have wires. When you have some wiring here, you have a thick layer of insulation. So the signal does not leak out. Same thing here. And if you don't have enough layer here, what is the disease that it's called? MS. Okay, it's called MS, right? Some people, they don't have enough myelin and the nervous system is not working well because the signal is leaking out. So it works like electricity. And guess what? That myelin is made of fat. It's made of cholesterol, animal fat. So we need fat for the system to work nicely, smoothly. Okay, let's do that. So that comes from the book I'm using without calculus book, but it's nice. So it has two 1.5 batteries, two. So that will be 3 volts. And then you have a load, boom, 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 boom. Ah. And then you go back to base. You can put a multiplication here. So you see that the voltage drop here, the voltage drop is just 3 volts. So the voltage drop, so Ohm's law says that the voltage drop between A and B, so this is A and this is B, equals the resistance of the load times the current going through it. It's very important that you remember it's a voltage drop. You're measuring, it's like measuring the height. So 3 equals R times 0.4. So resistance will be 3 divided by 0.4, which is 3, 1.2, 7.5. It has to be more than 3 because you divide by something smaller than 1. Okay. So 7.5 or ohms. Okay. Okay. So we have something about internal resistance. So I just want to remind you, if you have two loads, so you have a circuit with a power supply here, and let's say you have a resistance R1, and then you have a resistance R2. So that will be your circuit here. And that's what I did last time. We're going to use that schematic here. So that will be your power supply uphill, like altitude. You start with this, and then you go this way because you go with the current. Current go through here, and then it goes through here, and then it come back. So you start from the voltage. So let's say this is 9 volts. So let's say you 9 volt, and then you go boom, 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 boom. Nothing happened. Boom, you drop. It's a drop. You have to drop. And then boom, you drop again. And then boom, 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 you go back to base. So you're going to have a voltage drop here. So let's take example. Let's say this is, let's say R1 is 2 ohms. R2 is 1 ohm. Okay, and here, let's say it's going to be 3 amps. So what's the voltage drop here? 6. Do you all agree? Right? 2 times 3 is 6 volts. What's the voltage drop here? 3. Agree? So it means that you start with 9, you lose 6. Boom. You lose 6. How much is left? 3. So if you have more than 1, so if you have 9 volt and let's say boom and then boom and then boom, and let's say this is 2 volt and this is I don't know, 3 volt, and this is 4 volt, right? And you are measuring the voltage relative to the ground. You 9, boom, you fall by 2. How much is left? 7 volt. And then boom, you drop by 3. It's going to be 4. But you see, it's a drop, and then it's a drop, and then it's a drop. So voltage drop, you have to think of voltage drop. Okay? So inside the battery, everything happens like you have a little resistor hiding inside. It's not really literally hiding, but everything happens like it's gonna hide inside as the battery gets older. So to begin with, there is almost no resistor inside, and as it gets older, everything happens like you have a sneaky, hiding little resistor. So that means when you are measuring the voltage across here, which is called the terminal voltage, the EMF will be still 12 volts. So you have 12 volts, it's a car battery. Because of this small internal resistor hiding inside, you're going to lose some voltage. You're going to have a voltage drop across that little sneaky resistor, and you're going to have less voltage available to the load. So when a car battery gets older, instead of having 12 volts, you have 10 volts, and all of a sudden it dies on you. It did on me, but luckily it was for my astronomy class. It dies. Okay, 10 volts is not enough to start the car. So this is called internal resistance. Okay? So let's take an example here. And I will show you how to do it. Is the same thing, but it's hiding inside. And it depends, and it's gonna steal from you. So the terminal voltage will be the voltage you are measuring across the battery when it's connected to a load. When you have current flowing, your headlights, for example, are on. If you measure the voltage, it's going to be called the terminal voltage. If there is no load, it's called the EMF. So as the battery gets older, the terminal voltage gets smaller. So how are we going to do that? We're going to do 12 volt. Okay, that's what you want to start with. Inside here, inside the battery, you have a very, very sneaky resistor R of 0.01 ohms. You don't see it is inside, okay? You cannot open it. So this is closed. It's a closed box. That's your battery. And then after that, you have a load. Okay, it's another resistor. Headlight, I don't know, start plug, something like this. And then you have the current. In that case, you are draining 10 amps. Depends on the load that you have here, you are draining 10 amps. What's going to be the terminal voltage? So how much you're going to lose here? What's the voltage drop across here? So 12 ohms law, it's going to be 10 times 0.01, which is 0. 0.1. Yes, thank you. Volt. That will be the drop, yes? But how much is left here? Yeah, that's what we call the terminal voltage, because that's what it's going to be left to the load. It means if you come here, that's you, and you're measuring the voltage here. You are not a voltmeter, right? If you measure the voltage here across your battery, the car battery, you're gonna read 11.9 volts. Yeah, I wanted to go to art and I didn't like my drawing. But that's the idea, okay? So that will be called the terminal voltage. Even though the EMF is 12 volt. So how much is left for the load? Okay? And then do the same thing for 100 ohms, 100 amps. So do the same computation. So now you have a different load, and that load has more appetite. So how much, what is the drop here? 1. And how much is left? Exactly, 11 volts. So that's going to be the terminal voltage. It depends on the current, and the current depends on the appetite, and the appetite depends on the resistance. So if you have a smaller resistance for the load, you're going to drain more current. If you drain more current, you are losing more to the internal resistance. And that's what happened to your car battery. If you go to measure and the car is not on, you're gonna read 12 volts. Or you say, okay, it's good. So that's why they have other way to test the battery. I guess they attach a load to it and they see how much is lost. If you have left with 9.6 to 10 volt, you need to change your battery. Any question? Okay, so here's another example. You can help each other. So this is in a car. The car has a 12 volt battery, and so you have load like the starter, and the return path. The return path in a car is the chassis itself. Okay, there is no return path, like there is no wire. The way it coming back to the battery, it's the chassis of the car. But anyway, okay. Okay, let's do that. It's the same thing. So either you go to Costco or you call AAA. Okay. So when you say the voltage across the starter, that means the load. That's the load. Okay, so you start with a 12 volt. And here you have the little sneaky guy, 0.03. Okay, and then you have your load, which is the starter. And you have the base. And you have the current flowing from uphill to downhill. And you have a voltage drop of, yes, 3.9 volt, right? And how much is left? 8.1, right? So that will be the terminal. That means that means this. It means this. Not going to start because I don't know how to change the battery. And anyway, if you go to Costco, you have to call a Uber or something. So it will be the same. Okay. Safety. So again, it's the current that kills, not so much the voltage, because heart heart is a muscle. Okay, so safety here. About safety, the outlets, like everything in a building, in a house, the return path is the ground. So you don't want to build the return path. Okay, so this is not safe. This is safe because you have a connection to the ground. So why do they do that? So the issue with an outlet here is not like a battery. Battery, there is so much current you can drain. From the outlet, you can drain as much as you want. Okay, put your fingers inside and you see. Don't put your finger. But if you have a house, right? I didn't evolve since kindergarten. That's how I make my house. Usually there is a little chimney here, and then outside you have a transformer. So the transformer goes, I don't know, a few thousand volts to 120 volt, 120 volt for your house. And inside here, let's say you have a dryer or washing machine. Okay, so from here you have hot wire, boom, 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 boom. This one is hot. And let's say you just have a return path. The issue with that is that if you have lightning, zoom, what's going to happen? It's going to put your house on fire. So that's not good. So what they do is that they connect this, the return path is connected to the ground. Okay, so this return path here at some point it's connected to the ground. So the ground is the return path, which means if you are here and there is some leakage, it wants to go back to the ground and it doesn't want to go through that resistance here. No way, it's too much. Ooh, look at that. I have an easy path. So it's going to go zoom. Okay, so you're going to be the return path. So this is how you can get electrocuted. So that's why now those devices, they have another connection straight to the ground. So that way, if there is some leakage, maybe it will go through you a little bit, but some of it will also go through the ground here for security. Yes. So it's always taking the path of least resistance. So you don't want to be that path. So it's advisable when you are doing your machine, especially in Florida when they take so little care of the machine. You don't want to do it in flip-flop, right? Your bare feet, even worse. You never know. Not mole, I don't object electricity. Okay, so here you have the hot wire. The return path here is connected at some point to the ground, but maybe not that safe because you still have some voltage drop to go through. This is connected to the ground, so if you stick something inside there, you touch it, you're going to be safe because it's connected to the ground. Used to be, there was no connection to the ground, right? They were not very good at safety. Okay, so not good because if there is a leakage somewhere, boom, you are the return path. Are we good? So then we have the resistance of connecting wires. It's going to be proportional to the length, inversely proportional to the area, and it depends on the material of the connecting wire. Right? So if I have okay, so this is your connecting wire, like wires here that I have. If you increase the length, you increase the resistance, make it harder to go through. Decrease the length, decrease the resistance. Increase the area. You see, it's like you make the pipe wider, you decrease the resistance. So if you have connecting wires, wider is better because you're not going to lose that much energy to heat. Okay, so resistance turn energy to heat. Decrease the area, boom. Yeah. I don't know if it's a flow, but it's funny. Hey, we can make music, no? Can wake up students when they fall asleep because that makes the same thing. So, so anyway, you also have a constant here, right? So if it's copper, it's better than aluminum.